Hi class, this is Mr. Morris, and we are starting the last unit of AP Chemistry, Unit 9. And Unit 9 is all about just tying up kind of the loose ends of thermodynamics. So we talked a little bit about thermochemistry with enthalpy and heat and energy. We're going to wrap that up. There are actually a few laws of thermodynamics. There's the first, second, and third law, and there's one that we sometimes call the 0th law of thermodynamics. We're going to talk about those a little bit later. But today what we want to do is introduce a concept called entropy. You may or may not have heard of entropy before. But entropy is kind of a measure of disorder or chaos or randomness, so to speak. And the second law of thermodynamics is that the entropy in the universe always increases. So we always get more molecular disorder throughout the universe, not necessarily with every individual process, but our overall entropy is always going to be positive. It's always going to increase. So what that means is that entropy tends to increase with just general processes. That's a thermodynamically favorable process. It's going to tend to be one that has a positive change in entropy, where the entropy is increasing. So again, let's go in a little more detail talking about entropy. Entropy is a measure of molecular randomness and disorder or chaos of the system. One of the phrases that you'll see sometimes in AP Chemistry for you to think about is the number of microstates. So it's a measure of molecular randomness or disorder, or the number of microstates. We'll talk more about that, but a microstate just means a possible arrangement of a type of matter that you might have. So for instance, if you have a chemical reaction that takes place where you have more moles of products than of reactants, that's an increase in entropy because you have more possible arrangements, more possible ways that the products could be arranged than the reactants. Change in entropy of the system is represented by delta S, just like delta T means change in temperature, and delta H is the change in enthalpy, delta S is the change in entropy. The sign of delta S, so if the sign of delta S is positive, that means the system is becoming, you could say, more random or disordered. Okay. If delta S is negative, that means the system is becoming less random or more ordered, you could say. General rules for predicting the entropy of something are as follows, and these are, again, some of them are just kind of a rule of thumb, some of them are pretty reliable, but these are ways for you to think about entropy of a system without really even doing any math. So some of the AP questions, you need to be able to look at a scenario and decide, is entropy increasing or decreasing in this scenario? And here are rules. The general dispersal of matter, or the more spread out that matter is, the greater the disorder or randomness in the system is, the larger the entropy. Okay, so the more it spreads out, the greater the entropy. So thinking about something like volume increasing. If the volume of a gas, let's say, increases, the gas particles are spreading out more. That's an increase in entropy. If pressure decreases, that allows the particles to spread out more. That's an increase in entropy. Here are a few other examples. The entropy of a substance always increases as it changes from solid to liquid to gas. So a solid has the lowest entropy. Liquid is a little more, and gas has a substantial amount more entropy. And we could look at a PhET simulation of the different states of matter, and you would very quickly be able to see this, where solid particles are just kind of vibrating in place, and sometimes they're in a very structured environment. Liquid particles, they're close together and they can roll past each other, but that's about it. But a gas substance. The particles are bouncing off of each other, randomly hitting the walls, and then hitting each other and bouncing back and forth all over the place. It's a very random process. So you can see that entropy increases as we go from solid to liquid to gas. Tends to also increase just in general when you increase temperature. When a pure solid or liquid dissolves in a solvent, the entropy of the substance usually increases. There are some exceptions to that. But so the entropy of a solid is usually going to be less than the entropy of that aqueous substance. Well, that's almost always true. And also, the entropy of a liquid is usually lower than the entropy of an aqueous solution, even if it's an aqueous solution with liquids. When a gas molecule escapes from a solvent, the entropy increases. So think about like a soda. If you shake up a soda and you take the lid off, the gas escapes. It's coming out of the solution. That's more randomness. The entropy is increasing because we did have carbon dioxide dissolved in the soda, but now it's escaping and it's more spread out, and there's a lot more randomness in that process. The higher the molar mass a substance has, the greater its entropy would be. This is maybe one that isn't as intuitive, so you may want to just kind of try to remember that. In general, the higher the molar mass, the greater its entropy will be. And you can see a list of entropies here to just kind of justify that for yourself. Helium has a much lower entropy, for instance, than xenon, which is in the same group but way farther down. It's just a much larger noble gas than helium is. For a given state of matter, the entropy generally increases with the molecular complexity. So the more complex a molecule is, the more different types of atoms that are in a compound, the more spread out it is, the higher the entropy. So for instance, we have CO and C2H4. Their molar mass is about the same, but this is just 2 atoms. This is 2 plus 4, that's 6 atoms added together. So the molecular entropy is much greater for the more complex of the 2 atoms, of the 2 compounds, I should say. And you could see the same thing for these NO compounds and between argon and nitrogen monoxide. The more complex the molecule, the greater the entropy most of the time. In a reaction or process, compare the total entropies of reactants and the total entropies of products. So you're going to be looking sometimes at a chemical reaction, and you need to look at the total of the entropies. So overall, does it look like we're getting more random from the left side to the right side, or less random from the left side to the right side? If the entropy of the reactants is less than the entropy of the products, then delta S is positive, and the entropy of the system increases because I've got more entropy in the products than in the reactants. That seems to kind of make sense. Now, if the entropy of the reactants is greater than the entropy of the products, that means delta S is going to be negative. By the way, this is not a thermodynamically favorable thing. The entropy of the system decreases. All right, we're going to do some examples in the next video.